In this lecture video, we will be discussing reactions of alkene. And before we get going, let's discuss the chemical property and the reactivities of the alkene's functional group first. So we see that alkene are electron rich. And because they're electron rich, they like to donate electron in chemical reaction. And again, the reason why they're rich in electron is because within the double bond, there's actually two sigma electron in here holding the two carbon together to form this sigma bond. And in addition to that, there's also two pi electron overlapping between these two carbon right here to make up that pi bond. So they consist of two pi electron and two sigma electron, therefore 4 electron total. And because it is rich in electron, therefore it can behave as a good electron donator, in which it can act as the following. First, a weak nucleophile. And second, a weak base. So that will be the chemical reactivity of the pi electron in the double bond. And again, it is actually the pi electron that are reactive, not the sigma electron in the double bond. And alkene undergo in a class of reaction in which that we refer to as addition reaction. And in this addition reaction right here, there will be two groups that will be added to the two carbon across the double bond, and therefore breaking the pi bond as in this process right here. So again, this reaction right here, where the two groups are added to the double bond, are referred to as addition reaction. And this is basically how addition reaction would go right here. Before we go over the different types of addition reaction, all addition reaction share this very similar principle right here. So in all cases, the double bond are either behaving as a weak base or a weak nucleophile. So let's say here we have an alkene functional group. If we were to give this alkene right here to something that is a good electron acceptor, so let's say E plus here is a good electrophile or an electron acceptor. So this can be an electrophilic carbon or a proton. Both the electrophilic carbon and the proton are good electron acceptor. And now when they come in to react with the alkene, because the alkene are rich in electron, therefore the alkene will then be able to take the electron to donate electron to this electrophilic center right here. And one of the things that we would notice is as follows. So the electron are shared between the carbon 1 and carbon 2 here in this case. And as the alkene is behaving as a weak base or a weak nucleophile, here is how it can happen. So we can imagine the following. Either the carbon 1 will be taken both of this pi electron, come in, attack this electrophilic carbon. Or the carbon 2 that will be taken this 2 electron right here and come over here to attack this electrophilic carbon. If the carbon 1 were to take the pi electron and attack the carbon, then it basically will be taking one electron away from the carbon number 2. Therefore, the carbon number 2 will then become a cation. In the case that if it were the carbon 2 that now take both of this electron to attack the electrophilic center, then now carbon 1 will then become a carbocation. So in this case right here, we will be forming two carbocation intermediates. And again, they become carbocation because the double bond is giving electron away in the course of this attacking step right here. So we can either have the carbocation located on the carbon 2 or the carbon 1. Now notice how these two carbocation ions right here are not equal in terms of stability. The stability between these two carbocation intermediates are dependent on the R1 or the 4 groups that are connected to this double bond right here, which can make one of them more reactive than the other. And basically, because these two carbocation right here have different stability, the major product would be whichever that are more stable. So in this case right here, the major product which one that is more likely to happen would then depend on the stability. So the more stable intermediate. If the first one is more stable than the second one, then this would then be the major products. And again, we have to be comparing the stability of these two carbocation right here, on carbon 1 and on carbon 2. And once we form these intermediates already, then now we can see that this carbocation right here is a good electron acceptor. So therefore, if we were to have some sort of reagent in the reaction that can serve as a nucleophile, the nucleophile will then come in to attack this carbocation right here. So if we were to form the carbocation above, then now the nucleophile will be able to come in and attack this carbon right here. Versus if we were to form the other carbocation at the carbon 1 on this intermediate down here, then now the nucleophile will then come in and be able to attack this carbon right here. And as the consequence, then now the nucleophile will be added to carbon 2 in the case above, and down below, then now the nucleophile will then be able to add it to the carbon 1 and forming a sigma bond to this C1 right here. And one of the things that we notice here in this reaction is that the hybridization of the carbons in the alkene are changing in the course of this reaction. So in the case from original, now each of this carbon right here will then be sp2, and they are not chiral center. But as the reaction proceeds to produce this product over here, we can then now notice that both the C1 and the C2 have now changed into sp3. And now they may become center. So C1 and C2 here, again, dependent on what these groups are, they may or may not be chiral center, but they're both sp3. So may be chiral center. So that is the overall big view of all of these addition reaction of alkene. So let's go over the step again. First, because the alkene are rich in electron, therefore it can attack something that is a good electrophile, or it can be an electrophile carbon or a proton. And as a consequence, the alkene itself would now become a carbocation and therefore become good electron acceptor. So if we were to have all the reagent in the reaction mixture that can now serve as a nucleophile, the nucleophile will be able to add in either to the carbon 1 or carbon 2, depending on which of this carbocation intermediate would form. And again, because these two carbocation right here, depending on what R1, R2, R3, and R4 would be, they may have different stability to them. So the major product would then be the more stable carbocation intermediates. So that's the one that will form more. That's how we can figure which of this would form. And once they form already, and now they're followed by the nucleophilic attack, they now will be producing this two product right here. And so which of this product right here that would be major, either this product or this product right here, is actually dependent on the stability of the carbocation intermediates. And there's a variety of different addition reaction of alkene dependent on the two groups. So we can call one group the E and the other one the nuc. The other group is behaving as a nucleophile. So depending on what is the electrophile and what is the nucleophile, they're being added to the alkene double bonds. This reaction have different name to them as follow. So if we were to have a hydrogen and a halogen that being added to the carbon-carbon double bond in the alkene, this would then be referred to as a hydrohalogenation reaction. Whereas if we were to have H and OH being added across the double bond, this would be referred to as a hydration reaction, or simply addition of water to the double bond, because H and OH make up water. And if two hydrogen were to be added across the two double bond, then now this would be called hydrogenation reaction. And if we were to have two halogen being added across the carbon-carbon double bond. This will be referred to as halogenation reaction. And we can also have the halohydrin formation as well, in which we have an OH and a halogen being added across the double bond. And if the two hydroxy group that are added to the double bond, this is then referred to as dihydroxylation reaction. So all of this are collectively referred to as addition reaction of alkene, where the different groups are being added to the carbon-carbon double bond. And now, as these different groups right here are being added across the double bond, there's something that we have, the one factor that we have to consider is first the regioselectivities. So where did the group are getting added? Where did the electrophile getting added? Where's the nucleophile getting added? To carbon 1 or to carbon 2 of the double bond? Or their selectivity? And in some of this reaction right here, there's actually selectivities. So that's something that we have to be focus on, the regioselectivity of where the groups are being added. And second, the stereoselectivities. As we learn and perform addition reaction, we have to pay attention to the stereoselectivity as well, because initially the carbon as part of the double bond are sp2 and they're not chiral center. But once they undergo addition reaction already, they change into sp3 and now may become chiral center. So therefore, are there any stereoselectivity or not? That's something that we'll be discussing in this addition reaction as well. And the third factor would then be the carbocation rearrangement, because we can see that in addition reaction, we do form a carbocation intermediates. So is it possible that this carbocation will undergo rearrangement? That will be another aspect for us to consider as well. And now, as you may have already recognized, there's something that we have seen in addition reaction already. And if you can recall, yes, it's something that we have seen already. Addition reaction is basically the reverse of elimination reaction that we have learned before already. So these two reactions right here are the reverse of each other. So when we have a double bond and now we add in some group to it, going in this direction from left to right side, in this direction right here, this would then be addition reaction. And if we have learned about elimination reaction before, we can actually remove the hydrogen and the X here and making a double bond between carbon 1 and carbon 2 to now go back to the reactant side. And in this direction right here, this is then elimination reaction. Because addition and elimination reaction are the opposite of each other, they may be reaching equilibrium, in which equilibrium may be shifted to the reactant side, the alkene side, or the product side. And this equilibrium right here has been found to be temperature dependent. Yes, by controlling the temperature, we can either favor an addition reaction or an elimination reaction. And this is actually how it is temperature dependent. If we were to, let's say, calculate the delta H of an addition reaction. So in this case right here, we have a double bond and we are adding hydrogen and chlorine across this double bond to form this product right here. And in the course of this reaction right here, if we were to calculate the deltas of this reaction, we could then see that we are breaking a pi bond, a double bond between the two carbon. And we're also breaking an HCl bond as well. And on the product side, these are the two new bonds that are formed right here. A bond between the carbon and the chlorine, and the carbon and a hydrogens. And if we were to add all of this up, so the deltas of the reaction equal to the sum of all of the delta H of bond broken plus the delta H of all of the bond that are formed. But then now we have to notice that all of the bond that are formed will have negative value to them. So if we were to calculate this, the deltas of the reaction would then equal to 166 kilocalorie per mole. That's the sum of these two bonds add together. And now plus negative. When these two bonds right here added together, they equal to, again, negative 185 kilocal per mole. And now the deltas of this reaction right here is negative 19 kilocal per mole. So we can see that this is an addition reaction right here. And the delta H of an addition reaction is a negative value, meaning addition reaction are then exothermic. That basically means the reverse of this, the elimination reaction are then endothermic. And now because addition reaction are then exothermic, they are producing heat. We need to remove heat in order to push the equilibrium and favoring addition reaction. So this is why that by performing this reaction right here at cold temperature, that is how we can favor addition. So therefore we can see to favor this, we need to remove heat. To favor addition reaction. Therefore, addition reactions are normally done at low temperature by keeping it cool. And the opposite is then true for elimination reaction. Elimination reaction are then endothermic, meaning they require heat in order to favor them. So therefore, we have to add heat if we want to perform elimination reaction. So add heat to favor elimination reaction. And therefore, most of the elimination reaction are done at high temperature by keeping them hot. So that's how that the temperature can affect the addition versus the elimination reaction. So again, addition is favored at low temperature, while elimination reaction are being favored at higher temperature. So again, go in this direction. This is addition. And addition is done at low temperature. And the opposite, in this, the product going back to reactant, this is elimination reaction. And this would then be done of being favored at high temperature. So keep it cool if you want to add. That would be perhaps a good mnemonic to help us remember this. Keep it cool if we want to add.